So let's talk about how to integrate trigonometric integrals using Pythagorean identities. This integration technique is really a special case of the change the way it looks idea. So in first semester calculus, we changed the way it looks using algebra, but this time, instead of using algebra to change the way it looks, we're going to use trig identities to change the way it looks. Okay, so we really need to review some of the basic trigonometric identities. So the first ones we want to look at are the reciprocal identities. Reciprocal just means 1 over, right? So if you have secant of theta, that's equal to 1 over cosine of theta. If you have cosecant of theta, that's equal to 1 over sine of theta. And if you have cotangent of theta, that's equal to 1 over tangent of theta. So one easy way to remember these is that a co-thing is always paired with a non-co thing. So cosine is paired with secant, cosecant is paired with sine, cotangent is paired with tangent. Okay. Another type of trig identity that we want to look at is the quotient identity. Now, quotient basically means, you have a fraction of two things. So tangent of theta is equal to sine theta divided by cosine of theta. And we have that cotangent of theta is equal to cosine of theta over sine theta. Finally, we have our Pythagorean identities. Now, the classic Pythagorean identity is cosine squared theta plus sine squared theta equaling to 1. And what you notice is if you divide both sides of this Pythagorean identity by cosine squared theta, you would get another Pythagorean identity, which is 1 plus tangent squared theta, and that's equal to secant squared theta. All right. The final Pythagorean identity can be obtained by looking at the original Pythagorean identity, and instead of dividing by cosine squared, we're going to divide both sides by sine squared theta. And when you do that, you're going to get the identity cotangent squared theta plus 1 is equal to cosecant squared theta. All right. So let's look at an example and we can see how we can use these trig identities to really change the way the integral looks and then solve the integral. So when I look at example 1, I want you to notice that we have sine of x and cosine of x paired together, but I want you to pay special attention to the two powers. In particular, I want you to notice that this cosine of x has a odd power right there. Okay. So the first thing I want to do is I want to peel off one of those cosines from the odd power. So really, this integral is going to become the integral of sine squared x cosine squared x, and then I have the cosine of x dx. So I'm going to make a little note here. I'm going to say notice the odd power, and I'm going to say peel off a cosine of x. Okay, and we've just done that. Now, why is it important for us to peel off a cosine of x? Well, the real reason why we wanted to do that is we want to look at this piece right here, this cosine squared x. And what I'm going to do is I'm going to use my Pythagorean identity to replace this cosine squared x. Okay, so maybe I should, maybe I'll sort of highlight that. So let's look at this part right here. Okay, and what we want to do is we want to use the fact that cosine squared x plus sine squared x is equal to 1 to rewrite cosine squared x in terms of sine of x. Right? And we can do that just by doing a simple subtraction. So when we do this, we're going to have the integral of sine squared x. That part stays the same. But I'm going to replace the cosine squared x with 1 minus sine squared x. All right. Now we are in fantastic shape. Why are we in fantastic shape? Well, the reason why we're in fantastic shape is that this integral is now set up perfectly for a u substitution. In other words, I can let u be the sine of x, and then the derivative of u is sitting right off to the side here. So let's do it. We're going to let u be equal to sine of x. This means that du dx is equal to cosine of x, which means du is equal to cosine of x dx. Okay. So after I make this substitution, I'm going to have the integral of u squared. I'm going to have 1 minus u squared, and then the cosine x dx gets replaced with a du. Awesome. So now I simplify the integrand by distributing, and we're going to get u squared minus u to the 4th du. And at this point, I can find the antiderivative. The antiderivative of u squared is u cubed over 3. The antiderivative of u to the 4th is u to the 5th over 5. I want to make sure I put in my plus c. My original integral was in terms of x, so I can't leave my answer in terms of u. So I need to change that back. So that's going to be equal to sine cubed x over 3 minus sine to the 5th x over 5 plus c. And let's highlight our final answer like this. Okay. All right, so let's outline our strategy. The first thing I want to highlight is that we need one of our exponents to be odd. Okay. Then here's what our strategy is going to be. The first thing we're going to do is we're going to peel off a sine or cosine from the odd power. The second thing we're going to do is we are going to write everything else in terms of the other trig function. And the last thing we're going to do is we're going to use u substitution. All right, everybody, I hope you enjoyed this video. We'll work on some examples in class. Take care, everyone.